All right, so last example here. It says that the circular blade on a saw rotates 4,200 revolutions per minute. We want to find the angular speed in radians per second. So this time we actually have the desired label. So again, we know that we're going for radians per second. Again, we've got to wrap our mind around what it is that we're actually talking about. So again, a circular blade. We're talking about a saw, like a circular saw. Again, you push the button, you pull the trigger, whatever. Again, depending on what type of saw blade you're talking about, but it's going to cause the saw blade to spin around in a circular motion super fast. And again, saw blade is going to obviously be sharp. It's going to be flying around really, really, really fast, and it's going to be able to cut whatever it is that you're trying to cut. So what we're saying is that circular blade on that saw, it's going to rotate 4,200 revolutions per minute, meaning it's not like the clock. It's not like the second hand on the clock to where, oh yeah, it makes one trip around the circle in a minute. This one's going to rotate around 4,200 times in a minute. So obviously much faster pace here. Our job is to find the angular speed. If we wanted to find the linear speed, we could do that too, but we want to find the angular speed. So our given formula is that we're going to go that, excuse me, we're going to say that omega is equal to theta divided by time. So remember that we're told to go radians per second. So again, figuring out radians per second, that tells us, just like we did with the previous problem, we need to figure out theta. We need to figure out t. As soon as I know theta and as soon as I know t, then we can plug them directly back into our formula, and we divide it out, and we have it. We're all set. Now, again, that's the way that we're going to do the problem. But first, I think that it's just going to be a little bit better for us, or easier for us, to, instead of talking about this in radians per second, let's talk about it in degrees per second. Now again, rarely, if ever, would we see a problem of this nature in degrees per second. But again, why fight it? Most of us probably feel more confident and comfortable talking about degrees as compared to radians. So if we were thinking about this in the same fashion, we need to figure out theta, we need to figure out. So we know that, thinking about the angle here, if we were to take one trip all the way around that circle, that's 360 degrees. That would be one revolution. If we went 2 revolutions, all that we're going to take now is 2 times 360 degrees, and that's how we know that we have 720 revolutions. If we were to go 3 trips around, we would take 3 times 360 degrees, and that's how we would know that we're traveling 1,080 degrees. 1,080 degrees, that represents 3 full trips around the circle. And we could keep on going. We could figure out 4 or 5. We can figure out all the way up to 4,200. But it would be foolish, in my opinion, and hopefully you agree, it would be foolish to keep doing it this way. Instead, let's do the multiplication. We can take that 4,200, multiply that times 360 degrees, and what that's going to give us over here is 1,512,000 degrees. Okay, got it. Now, time, if we're thinking, yep, time takes us 1 minute, 4,200 revolutions per minute, yes, I agree, but our target, as we can see, is radians per second. So instead of calling this 1 minute, we want to be certain to talk about this time in relation to 60 seconds. So now that we have theta and time, we're going to plug into our formula. As you can see, formula is up here, theta divided by time. So again, now it's just a matter of building the case here. So when we plug in theta, 1,512,000 degrees divided by time, which was 60 seconds, we could do the math, we could clean this up, and we could be successful, absolutely. But our job was not to find degrees, instead of radians. So the only difference, and now I'm kicking myself for erasing this, the way that we found that theta was 1,512,000 degrees, remember, is we knew that we weren't taking one trip around the circle, but instead 4,200, and that's what we multiplied times 360. That's how we got there. So when it comes to radians, the way that we're going to get there is we're not going to use 360 degrees. We know that one full trip around the circle is too high. So what we're going to do is recognize that we're not taking one revolution, but instead 4,200 revolutions, multiply that times 2.5. That's how we're going to be able to say with a lot of certainty that theta is equal to 8,400 100 pi. This will be the numerator of our formula, of our fraction. Same story with t for time. Again, we know that the target was radians per second, so we're still going to say, oh, that'll happen in 1 minute. So again, t is going to be equivalent to 60 seconds. And from here, hopefully it looks pretty familiar. It's just the case of now building the formula. Omega is going to be equal to 80,400 pi, and that is over 60. Remember, we can take care of the labeling right now. We know that this is going to be in radians per second. We're there. We just now need to clean up the numbers. So as we do a little bit of reducing, I suppose, 8,400 pi over 60, that's going to clean up to be 140 pi. Again, radians per second. This would be our exact answer. If you're thinking, could we, do a little bit of work and get that in terms of, more like a decimal answer? The answer, of course, is yes. We could do it that way. But again, this is perfectly fine. Like I said, it's exact. Directions didn't say anything's wrong with an exact answer. Rarely is there going to be something wrong with the exact answer. All right, so the goals that we had in mind were that we wanted to be able to describe angles. Again, thinking about coterminal, complementary, supplementary, positive, negative, all that type of stuff. Absolutely, which quadrant are we in? Again, that sort of thing. I think that we can describe some angles. Students be able to use both degree measures and radian measures. Like I've said a few times now, I'm fully aware of the fact that we all feel more confident and comfortable in degrees as compared to radians, but that's a work in progress. But I think we're there. Again, as long as we know how to convert, that means that, in terms of formulas and things like that, if you're given the wrong, shouldn't even say the wrong, but if you're given one angle measurement and you wanted the other, we could always convert it back. And then finally, third goal, what we were focusing on most recently, students be able to use the angles, or be able to use angles, I should say, to model and solve real-world problems, especially with that circular velocity. Again, work in progress, but I think we're getting it. So that mandatory portion of the assignment found on page 269, that's going to be due tomorrow. Like I said in class, we did cancel the worksheet, so if you were wondering where that worksheet is, that had been written about on the Google Classroom. Again, we are not going to do that at this time. We're actually going to do it at a later time, but again, not right now. Other than that, have a great night, and come see me if you have any questions.